The next speaker is Professor Neiman from Okinawa. Where is
hello,
your...
everybody. Just a second. So connecting from the convenient place. What I wanted to tell you about is a kind of meditation on a pair of good and old papers by Slava Didenko and Misha Vasilyev from 2008, 2009. Where they introduced this black hole-like solution of four-dimensional Higherspin gravity. And in a bit more detail, they accomplished there a series of three things. So the first is a procedure for generating solutions of linearized Higherspin theory out of some twistor functions. So the idea is that if we want to create a master field, so this scalar that depends on space-time and spinor variables, which encode the spin's polarizations and their derivatives, then we can construct one that solves the free field equations.
I'm sorry, do you see the screen? Can you see what he's writing? I think it's too far.
It's a little bit too tiny, right? Thanks, Augusta. I was about to say it like the same. So can you please write maybe with larger letters?
Maybe there is a way to amplify the view from the camera.
Yeah.
Yes. Oh, yeah. Okay.
And
how about
have to move it, but this way it's doable.
Okay. Let's see. So we out, move. Okay, we have one board that is reasonably zoomed in. Okay, so switching to writing here. So we have a procedure for generating solutions to the Higherspin field equations at linearized level, which is taking in a function that transforms in the joint representation of Higherspin algebra and is covariantly constant with respect to the Higherspin connection, and do some operation on it, star product with a delta of one of the two spinners, and this generates a linearized solution. So the second part of those papers is that there is a particular choice of this function f, which gives us the linearized fields of a point particle source. Okay, and to say what this choice of function is, So I'm going to work for convenience in Euclidean ADS. Four-dimensional, it looks like hyperboloid in 5 dimensions. And in order to put a point particle source, we need to place it on some geodesic, okay, in Lorentzian, a time-like geodesic, here a space-like geodesic in the bulk space-time, joining 2 boundary points together. And the time translations along this geodesic make one of the generators of the space-time symmetry group. So if we denote the corresponding directions in embedding space by L and L prime, then we can construct the generator of these time translations as the plane element that contains them normalized. And so the choice of function that gives us the linearized fields of this point source is roughly exponent of this generator transformed into twistor indices with gamma matrices times 2 twistors. Okay, so this gives us linearized fields, which in particular can be thought of as a linearized version of a black hole solution. So it generalizes the linearized version of Schwarzschild. And then in the final step, it turns out to be possible to extend this in analogy to the way the Schwarzschild solution can be extended from Kerr-Shield form to a nonlinear solution of the Vasilyev equations. And this solution is termed a higher spin BPS black hole, okay, where the words black hole are a bit metaphorical. We know nothing about an event horizon or such, but the word black hole BPS is quite literal. So this is a solution which in the supersymmetric case is literally BPS, and in any case is like the satisfies the analog of BPS conditions, the maximal preservation of the symmetry, just with supersymmetry replaced by higher spin symmetry. So it's higher spin gravity's analog of a BPS solution. And this is, in principle, a big deal, right? Because in string theory and supergravity, BPS solutions play a very key role in the whole structure of the theory in helping to connect the supergravity level description to the string theory and the D-brane level description. So we have solutions, BPS black hole-like solutions of supergravity, which then correspond to the various extended objects of string theory. Now, higher spin theory sits somewhere in the middle between these two. It is supergravity, but more because it has a larger multiplet of massless gauge fields and the larger gauge symmetry connecting them. And it is string theory, but less, because it is trying to be a complete theory of quantum gravity, to have a holographic dual, etc., but without the heavy modes of string theory. Okay. So we should be really interested in the question of how do these BPS solutions of higher spin theory behave. So, for example, in supergravity, there is this important property that if we place two BPS objects at rest in parallel to each other, then the force between the two is zero. The electric repulsion is precisely balanced by the gravitational attraction. So can we say something about the interaction between these BPS objects in higher spin theory? More ambitiously, can we figure out what they are made of, sort of what sits at the central singularity, where in the supergravity case, we can usually associate it with an important fundamental object like a fundamental string or a D-brane or such. So can we get a grasp on the physics of these BPS black holes, given that working directly with the nonlinear Vasiljev equations is not a very fun and easy task. So let's try and ask the simplest form of the question. So what is the interaction between the linearized versions of these objects? Okay. So the linearized solution itself is a solution of the Fronsdal action of free massless higher spin fields with something like gradient of higher spin field squared plus more terms with different arrangements of indices and traces, etc., summed over all spins. And to this, we can couple a point particle source, where there is an integral along the particle world line with S for spin S factors of the for velocity, multiplying the spin S potential and integrated along the world line. So this theory is not completely consistent as it stands in linearized form, just like linearized GR. With a source is not consistent. We need the nonlinear interactions to take care of the non-abelian gauge symmetry. But at linearized level, it is perfectly fine so long as we take the world line of the particle to be a geodesic. Because if it is a geodesic, then to leading order, the stress energy tensor is conserved, and so are the corresponding currents of all higher spins. Okay, so
is such a coupling is gauge invariant as a linearized level?
The current itself is gauge invariant at the linearized level, yes.
Okay.
All right. So a single linearized higher spin BPS solution is a solution for the fields for this theory with a single particle source. And now we can take a pair of them, okay, a pair of world lines sitting somehow in space, and as usual, calculate the contribution to the action from the fields of one particle acting on the other. Okay. And this is a question that can be asked already in Minkowski, or if we are in Euclidean signature, so simply in flat space, and then can be extended to ADS. So in particular in Minkowski, we can look at the simplest case of parallel world lines at rest with some distance b between them. And then we, of course, find that the action is proportional. So all the potential energies will be 1 over b. The action involves a time integral, so it will be proportional to the infrared cutoff, how long a time we are looking at. And then there will be some sum over the charges of these particles under the different spin fields. So with some nice conventions, there is the spin 0 charge, the coupling to the spin 0 field with the factor of half, because it has 1 helicity instead of 2, and then sum over all the other spins of charge squared with respect to spin s. Okay. Now, in the special case of BPS, where we only have ordinary BPS in supergravity, when we have only spin 1 and spin 2 charges, this goes to 0. Okay. So we can ask what happens for the Didenko-Vasilyev solution. Well, in order to figure that out, we need to understand what is the relative normalization, how to read off the relative strengths of the charges of different spins, okay, which is not immediately obvious from the just the structure of the master field. Okay? The master field is given at the level of equations of motion, not action, and from linearized equations of motion, you cannot read off these normalizations. However, we understand that just as in supersymmetry, the pattern of charges is determined by the preserved supersymmetry, here as well, it has to be somehow determined by Higherspin symmetry. So the way we can do that is to consider, first of all, zoom out from the Vasilyev-Didenko solution and consider again this general construction of linearized solutions from twistor functions. Okay, here I cheated a bit and rewrote it in my favorite way, where the x dependence is moved from the twistor function f into the delta that is transforming it. And so we have now this mapping between twistor functions that are now literally x dependent rather than just covariantly constant into solutions of linearized massless field equations, okay, which is just called the Penrose transform. Okay, so we can now consider this for our favorite solutions of massless field equations in ADS, where the simplest ones are simply boundary to bulk propagators, where we set the source at one point on the boundary and it induces a free field throughout the space-time. And we know that here at spin, there is a unique quadratic form, unique two-point function, whose normalization is given by the bulk action of the field. Okay. On the other hand, at the level of Higherspin algebra and the twistor functions here, there is a unique quadratic form that can be written down, which is the Higherspin trace of just the star product of the two functions. Okay. So by demanding that the quadratic action of fields of all spins is described in general by this Higherspin symmetric form, we can work out the normalization between the master field C that shows up in the Vasilyev equations and the canonically normalized Fronsdal field F, H, that showed up in our action before. Okay, so from that, we can read off the correct values of the charges. And going back to the force between two of these Higherspin BPS particles at rest, so we had action being L over B half Q0 squared plus some QS squared. And this turns out, just as in the case of ordinary BPS, to be 0. Okay, but it turns out that the result in the Higherspin case is actually much stronger than that. So we can consider a pair of these black holes / particles that are not mutually at rest, but that sit at some relative velocity or space-time angle with respect to each other. So in this case, the action is still divergent, with the size of our box divided by the impact parameter, the closest approach between the world lines. The divergence, the divergent part of the action is now logarithmic rather than linear, because the world lines diverge from each other, but it is now given by a different expression, where here every spin appears with a cosine reflecting the different tensor structure of the field. Now, the amazing fact about the particular pattern of charges of the Didenko-Vasilyev solution of the Higherspin BPS is that this turns out to be 0 for all angles except pi. So the only case in which the action is divergent is if we have a particle and an antiparticle at rest with respect to each other when all of the forces add up. Okay, so in the Higherspin case, as opposed to the supergravity case, we have a cancellation of these UV divergences when the particles come close together at any relative velocity. So here we are actually seeing non-locality as a good thing, as I was just heard Misha commenting a few minutes ago, where just as in string theory, the non-locality of the string, for instance, regularizes the interaction between d branes even if they intersect. And so here,
sorry, 5 minutes.
Very good. So here, even though everything we have is nominally local linearized interactions at every spin, when the entire tower is added together, the divergences all go away. Okay. Now, the same story extends to ADS, where we, if we have two world lines, so now they, in any case, diverge from each other at infinity because of the warping of the space-time. So we don't need an infrared regulating box. But if they come very close together, then for each spin separately, we will have the same infrared divergence as in the Minkowski case. But they all cancel out, and we get a finite result for the interaction action, which is something like cosh of the hyperbolic distance between the world lines and the cosine of the relative angle between them. Okay, so we have answered to some extent the question of how these seemingly singular objects interact with each other, finding that the interaction is actually smeared out and all UV divergences are regularized by the Higherspin multiplet. And now let me quickly address the question of what is this solution or the singularity at the heart of it, what is it made of? And one way to think about it is to start out with the solution in ADS, with the singularity along a geodesic, and start bringing the two boundary points of the geodesic closer together, so that the geodesic sticks closer and closer to the boundary, until we have a situation where the geodesic is very small and the boundary points almost join. Okay. Now, if we look at the fields of all spins that are radiated by this object at large distances in the bulk, they simply look like boundary-to-bulk propagators of a point of this point-like source on the boundary of all spins. Okay. And it turns out that the correct interpretation of the object itself is, so we have the this tower of operators of all spins on the boundary that is radiating all these fields. Is quadratic in the fundamental fields in the boundary vector model with mu derivatives between them, orderings, etc. And this can be viewed as a Taylor expansion of this simpler bilocal object, which is the product of the fields of the vector model at 2 points. Okay. And it turns out.
Sorry, 1 minute.
Yes, 1 minute.
Okay.
I suggested a couple of minutes from the technical break because there was some in the beginning. There was some.
No, I did shift 10 minutes.
All right. So it turns out that we can make this statement precise and construct a dictionary between twistor functions and boundary operators such that the endpoint correlators of the boundary theory are now calculated by these Higherspin invariant forms of different orders and actually demonstrate that the twistor function that yields the Didenko-Vassiliev solution plays precisely the form in the correlators of the boundary theory that is expected of this bilocal operator. So what is this like in string theory? In string theory, we have the spectrum of the string, which looks like an infinite series of point-like particles that is dual to point-like operators in the boundary gauge theory. And when taken together, this becomes completed into the string itself. And the string itself is dual to a Wilson loop in the boundary gauge theory, from which we can reconstruct all the point-like operators by shrinking it to zero size. So in the same way, this role is played by the bilocal operator in the vector model, from which we can reconstruct all the local operators by shrinking it to zero size. And so the final statement with which I'll leave you is that the BPS black hole, or so-called black hole of Higherspin gravity.
Sorry, we don't see.
Yes,
sorry, we don't see.
Focus.
Don't see it?
Defocused.
Okay, then I will just say it in words. That the BPS
No, it's
object,
good again, by the way.
Sorry?
It's okay again. I mean, it's focused.
Okay, that the BPS black hole of Higherspin gravity, it is actually the analog of the fundamental string in string theory. So it is the bulk image of the non-local boundary operator that completes the infinite tower of local ones. Okay, and so just as the string is both a new object and simply the sum of its fields, of its spectrum, so the Didenko-Vasilyev black hole is both a new object that isn't just made of the Higherspin multiplet, but at the same time, it is just the completion of the Higherspin multiplet.
Okay, sorry. Please go to conclusion.
Yes, done. Thank you.
Okay. Thanks to speaker for interesting and very exciting talk. Please, any questions? Very short, one very short question.
Anna Maria wanted to ask.
Well, so just naive question. So you're discussing at some point, as I understand, Didenko-Vasilyev black holes in Minkowski space, right? Interactions of them.
Yes, the linearized ones make sense in Minkowski as well.
And okay, and so is it true also for Higherspins that linear solutions get promoted to nonlinear ones?
Well, in Minkowski, we don't know any such thing. So the Minkowski case is just kind of a toy version of the more complete calculation in ADS, but it does provide, if you want, a hint at the possibility of the theory to exist in Minkowski, because we do get the finite interaction action in Minkowski as well, despite the world lines not diverging from each other as fast as they would in ADS. So if we are maximally optimistic, we can think of this as a hook towards developing the Minkowski theory. So I am slightly less optimistic than that, and I am merely viewing the story as a hook towards better understanding interactions in ADS, because since these objects correspond to the bilocal operators on the boundary, from the bilocal operators we know how to construct the entire partition function. and the boundary, which also includes bulk interactions. And maybe there is something useful to learn through there.
Okay, sorry, let's stop and maybe delay to discussion session. So thanks to speaker again, and he should go to the next speaker.
Right, thank you very much.
You are ready?